Hello and welcome. My name is Juliet, and today with Araceli, we will be discussing technology for detecting structural damage in post-disaster environments.
The main objectives of this project were to research different ways we could use technology to analyze structures and to help with data collection in post-disaster environments, and also to understand how we can apply this knowledge to the context of EWB. In many cases, after a large natural disaster, such as the 2010 Haitian earthquake, there's an influx of volunteers and agencies coming to the affected area to help with recovery. However, this can make coordination between the different agencies difficult, and for that reason, there needs to be standardized methods and good organization in place in recovery. In addition to rapid response to the disaster, there's also needs to be long-term support for the affected area. And for that reason, EWB focuses on community-based approaches, so involving the community in order to promote long-term relief and sustainable solutions for the area. We were inspired to pursue this topic after researching the disaster response on the island of Dominica after Hurricane Maria struck the island in September of 2017. So 20 EWB-USA members were sent to the island to work alongside the UNDP and local volunteers to assess the structures, damage done to the structures on the island. This was achieved through the use of an application developed by Microsoft and tablets donated to the island to be used for assessing the damage. And because this was done using technology, the data was able to be collected within 3 months, whereas if this had been done manually with pen and paper, compiling all the information would have taken at least 6 months. And in these 3 months, the 30 teams were able to assess the damage done to 30,000 structures. The name of this software was the Building Damage Assessment Application, and it allowed local volunteers to record what kind of damage was done to the structure, take a picture of it, and then the data was then uploaded onto a database. And if the tablet was offline, the data was synced to the database when the tablet was online. And the professionals could then analyze the information, review the data collected using Microsoft's Power BI software. And with this information, local organizers and local government could estimate how much repairs would cost or where the concentration of damage was and so forth.
So, to get to the importance of why this technology was so relevant to Dominica was because it allowed the government and local organizations to act quickly. Acting quickly was critical because rebuilding was a priority for the people in Dominica, one that other organizations might not necessarily realize. Thus, having this quick action and generating this recovery plan allowed to save money and save resources and allowed people to get back into their homes as quickly and efficiently as possible. Yet, now that we know more about the project in Dominica and the very high-tech software that they had access to, we found that this software wasn't necessarily available, and especially information about it was hard to find, which leads us to a question about how structural assessment is actually being conducted today. We found that most structural assessment actually happens manually. This is because of the fact that previously we simply didn't have the technologies to allow for more technologically based structural assessment. However, this comes with a slew of problems as well. One of the biggest problems is the limitations that come with having different people conduct these structural assessments. Different people have different levels of skill. They have different abilities to see structural impediments. They have a larger risk of being hurt or damaged when they're in scenarios or situations that might lend themselves to creating hurt. And also, when you have a range of inspectors, you have a lack of specialized knowledge that make the test as reliable as it needs to be. So having these structural assessments being conducted by humans is something that can definitely be improved on in this arena, which leads us to ask what other methods are available for structural assessment. One is that we looked into was the use of drones for structural assessment. So, as we mentioned previously, especially in a post-disaster scenario, most of the buildings where people want to see exactly where the structural impediments are also buildings that have serious damage to them, meaning that putting a human being there is not necessarily the safest thing to do. And that's where drones come in. Drones or unmanned aerial vehicles can be used to collect data, and more specifically, they can be used to collect photographs that can then be assessed later on. However, different groups that have used drones previously for structural assessment have come into the issue of having too many photos and then these photos being time consuming in themselves to sort. Now, this is especially pernicious in a time sensitive scenario like a post-disaster scenario like the one we found in Dominica. So there needs to be solutions for this as well. Luckily, there are. One solution is focused photo collection. The idea behind focused photo collection is essentially that you have a pre-planned flight path for drones and that this flight path is updated when drones return with photos in order to focus on the places where serious structural damage actually occurred. But this system just doesn't stop there. It's also speculated, or rather, people are coming up with ideas that would allow it to systematically generate reports that would then be reviewed by structural engineers. This would significantly cut down on time, and if engineers are able to continually fix the program to make sure that false positives on inspection reports were corrected, then the system would only get better and better. One example of using this focused photo collection took place in L'Aquila, Italy, and you can see in these images how drones narrowed down significantly the places that needed to actually have focused attention on. So as the previous slide displayed, this project was done in L'Aquila, Italy, and it had very spectacular results. We found that it was able to reduce the images that needed to be looked at by almost sixfold, saving a huge amount of time. And when you're in a disaster-related scenario, saving time is critical. So the image in the top corner shows the picture of the building that had the experiment carried out on it. The image in the bottom corner shows the machine that was used to simulate these earthquakes, and the image on the right shows the specific locations where the measurements were carried out.
The next method we looked into with regards to structural assessment after disaster is Lidar mapping. So Lidar stands for light detection and ranging, and it's a method that uses lasers to measure the distance from the surface of the earth to the aircraft. And with this information, one can generate 3D models of the surveyed land and be able to detect differences in height. Researchers found that LiDAR surveying was very effective in detecting structural damage after the 2016 earthquakes in Japan. So they were able to make this conclusion because 2 earthquakes struck the city of Kumamoto within 28 hours of each other, meaning that because LiDAR surveying was used after the first earthquake, there was baseline data that they could compare um, with the LiDAR surveying from after the second earthquake. So they found that the LiDAR surveying was able to detect with 93% accuracy structures that had lost at least half a meter in height. And so their conclusion was that earthquake-prone cities should regularly conduct LiDAR surveys in order to have data that they can compare with after a disaster. So these images show 3 different structures in the city of Kumamoto and shows how how the Lidar surveying was able to detect the changes made to these structures after the second earthquake hit the city. So the red signifies a increase in height, and the blue signifies a decrease in height. So you can see how each of the diagrams accurately represents what occurred to the buildings.
So now that we know about all these interesting methods, the next question is, are there any software that currently exists that can actually apply these improvements? And the answer is yes. So two researchers at the University of Nebraska this year came up with a software that kind of combines everything we've talked about so far. So it uses 3D renderings that are created from images collected by drones. And these drones are not just collecting images, they're also using LiDAR to kind of create more accurate depictions and more accurate models. And this is really cool because they can collect data not only in unfavorable conditions when thinking about what is safe and unsafe for humans to be in, but also unfavorable conditions when you think about where there's not enough light or there's rainy weather, because you don't always have perfect sunshine when you want to assess a damaged building. In fact, oftentimes it is the opposite. And what makes the software really interesting is that it has an extensive range of abilities to recognize patterns. So it doesn't just do structures, it can do vehicles and it can do bridges, and also it knows about a lot of structures. So that goes from temples in Nepal to just regular office buildings in Nebraska and Texas, and it's continually being updated. Just to get it started, it took 4,000 gigabytes of data. These are just a few examples of photos that were used when building up the software. So now that we know about this interesting methods and this amazing software, we have to ask ourselves, is this actually feasible for EWB to use? And how can EWB kind of improve its approach to disaster relief with these methods? So one way that we specifically thought about with regards to our project was the analyzing of a tank in Los Angeles. So while we wouldn't necessarily use drones to analyze a tank, taking photos and using LiDAR could have been a very interesting way to kind of double check our calculations when it came to whether or not there was any deformities in the tank. And it would have given us more information than we were able to get from just having one person in the tank taking photos for a long time than analyzing them when we came back. Additionally, any project that is EWB related or not could use these methods to examine structures. However, one thing that is extremely important to consider is the actual feasibility. So when we were doing the research for this project, we had a hard time necessarily finding the software that was already available on the market. Even the University of Nebraska project is still being commercialized today. And once projects like the one at Nebraska is completed, the next question is, how much does the software actually cost? Is it going to be feasible for teams to budget the software into their already pretty tight budgets for going on trips? And finally, and most importantly, how portable is the software? This doesn't mean how easy is it to get it from, say, Cambridge, Massachusetts to Mkutani, Tanzania, but it means when we're in the ground, when we're on the ground and moving about, how easy is it going to be to actually use the software and not be relegated to doing something else? All of these questions are critical to think about as EW moves forward in kind of rethinking the way that it does, or that it approaches structural assessment in post-disaster scenarios.
So, apart from the technical aspects of collecting data and assessing structural damage on a massive scale, there's also the importance of having strong organization and having strong tools in place so that the team can be as effective and as efficient as possible in their recovery efforts. So, one of the reasons why the Dominica Disaster Response was so effective in terms of collecting all this data was that they used the local talent. And so, because they were able to involve community members, they were able to have people who were directly affected by the hurricane and thus were very driven to help the area recover, and also have people who are familiar with the area be involved in the recovery efforts. And we also learned that it's really important to have multiple backup plans. So the Dominica team did have paper and pencil ready in case a tablet malfunctioned or there was no power available, and so forth. So it's important that members are trained and have a plan ready in case they do face a disaster, or if their original method is unable to be carried out and they have to resort to a different method. And all of this applies to smaller scale disasters. Also, no matter how big your disaster is or how big the team is, it's important to have all of these tools in place so that a team feels ready to take on a challenge if they are faced with it. So that concludes our presentation. Thank you for listening.